I think everything is up. Yeah, it's.
Yeah.
The presentations are already there.
Mm-hmm.
That's the first one.
Mm-hmm.
Okay. Hello, good morning, everyone. I'm Luís Correia with IST, the University of Lisbon, and it was a pleasure to accept Mukherjee's invitation to be the chair of the keynote session this morning. As you know, we have two keynotes with a balance in between industry and academia, as I think we should have in a conference like this, and also a balance in between regions, continents, whatever you may call it, and also the areas that we'll be listening to this morning. So a little bit of diversity is always a good thing. So the first speaker is Walter Weigel. I hope I pronounced your name correctly. He comes from Germany. He was, I'm not going to read his CV all along. You have it in the program. As you know, he took a PhD from a known university in Munich, right? Technical University in Munich, which is one of the well-known universities in Germany. And then he had a career in Siemens, but then some years from now, he has been a vice president for the European Research Institute with Huawei. So I'm sure he's going to tell us a lot of things about use cases and 5G and all these things. So Walter, please, the floor is yours. Thank you.
So good morning from my side. Thank you very much for the invitation. And you see the title. I don't give a whole overview about where we stand in 5G research. We are currently about 2,300 researchers in Europe doing, I would even say, most of the research within Huawei for 5G. And we have started to think what comes after next. I want to concentrate today on what we call the vertical applications. So I have several examples from 5G in use cases for cars, health, and industry, and I wanted to share with you a little bit what we are doing here. The credit of all the slides, I have to say, goes to Josef Eichinger, who many may know, and his team, because obviously as VP, I don't do the research not anymore myself. I think you all know very well this slide. So the goal was about latency, the 10 gigabit per second per connection, the 1000K connections per square kilometer, for high-speed trains, 500 kilometers. So at the end of the day, I think our goal was, all of us, I'm not only talking for Huawei, also Nokia, Ericsson, all the colleagues, that we can enable vertical applications like smart manufacturing, connected cars, high reliability, low latency, but with the 10 gigabit per second also to have, for instance, in the future, instead of the mobile phone, classes with virtual or augmented reality. Now, from 3GP, you may very well know what are the key parameters, and I don't read out all of them. Now, as we went into applications and some field trials, and you will see photographs, then it turned out that maybe some of our assumptions were not yet sufficient. So in the red bar down here, you see that we were confronted from what I call Industry 4.0, the German term for factories of the future, from colleagues Siemens, Bosch, ABB, and so on, that they said 5 nines for the availability. That's not enough. We need 8 nines. So here, very low jitter, and the 1 milliseconds latency we planned, they also said this may not be enough for our purposes. Please reduce it by half. So my message is here, when we are now coming into the real application of radio technology and cellular networks for vertical application, then there are some lessons to learn. This slide you may also know, IMT 2020 and beyond, the original one with the 3 main cornerstones, mobile broadband, which is not today my topic, so I'm looking on the massive machine type communications and the ultra reliable low latency communications. And many of you are working on the new air interface. We are more or less near to a product next year from many companies and the new architecture. And I will later come back to this one because also I think here are some lessons to learn. Now, vertical industries from our point of view That's now a Huawei view. We are looking into transportation, and here are some examples of transportation, like drones, passengers, goods within a factory. By the way, this is not a submarine. This is, you see here the sources, this is from Rolls-Royce. They are looking into autonomous cargo ships. And the others are health. So you will see industry, you will see a little bit, and we are also looking into energy and finance and insurances. Now, what are we doing? Many of our colleagues are based in Munich, and we are actually currently, besides the 5G PPP contributions, and I is here, we are doing research which is supported first of all by the German Ministry of Transport, the biggest field trial for autonomous cars. This is a map of Munich, and this is the motorway going out to Nuremberg. And they have decided, because it's high speed, very dense traffic, that this is the most challenging site in Germany. We are working with the Hospital of Technical University Munich, where the project is supported by the Bavarian Ministry of Economics. And you see, we have also many other sites, so our German regulator has given us test frequencies so that we can do real field trials. Now, very shortly again, so smartphone, that's relatively not simple, but it's a clear direction. It's broadband. The problem with the vertical applications like connected cars or mobile robots is that you have multiple, like broadband, low latency, high reliability. You've seen the figures from the industry people, and even contradictory service, and we have to support this at the same time, and this is obviously not so easy. Without going into details, you will get the slides, they will be published. But we had even a look in, if you want to support autonomous cars, what can be simple scenarios. So either you have a full coverage, or you have some ITS band, and you have here car-to-car communication, or you are outside of a cellular network, and then you can only rely on a non-assisted car-to-car communication, because in this case you may use the control plane of the backbone network. So when you see the description and then the different challenges, only a few examples: very short latency, additional network loads we would not have otherwise, then nevertheless mobile broadband for the infotainment, a signaling overhead, a dedicated band, and so on. So this is quite challenging to fulfill. So what we have done is, these are photographs from field trials near to the A9, not yet in real traffic, on the daily traffic. So this is from the 5G site links, so car-to-car communication, line of sight scenario, as you can see, but also we tried non-line of sight. And what we are doing is we are using a near-to-product research system, which is very flexible, so we can adjust the numerology. You see here different parameters, cyclic prefix, and the TTI interval, and so on. And so we tried experimental, what can we do? And what you see, some of the key results are here. So without retransmission, only one way, we achieved at least 4 nines reliability. We could, oh yeah, and I should say we were at 2.8 gigahertz for the site link carrier frequency. Maximum distance, we reached 1 kilometer. We accelerated the cars up to 170 kilometers per hour, and we measured end-to-end latency 0.7 milliseconds. What, to our surprise, happened is that nevertheless, not all of the tests were working perfectly. And you know what? It turned out that the computer units in the cars, they take a lot of time because they're not optimized yet to this kind of real-time applications. And so some of the car manufacturers, the OEMs we are working with, are now rethinking how the architecture of the, so to say, CPU in the car has to look like. This is now more technical. This is the UU, so the link to the base station. Here, our prototype with the different parameters. We also think that the antenna technology, we'll come back later, plays a crucial role. So currently we are using at the base station 8 transceive, 8 receive, and at the UE in the car 2.2. So we are trying to find out how the end MIMO antenna systems can help. Here's some simulation verification, and here for the data channel, so the error rate was quite outstanding. And this is, by the way, a comparison between turbo and polar code. And you may know what happened in 3GP. This is a little bit a pity, but okay. So from our point of view, polar code was, in this kind of scenarios, a very good choice. Now, shortly about vehicle speed. So here the test area near to the A9, and this is over the time, so we accelerated, here's the speed, and we looked at the error rate, and you can see this is that about up to 160, 170, it is quite good. And so we were quite positively surprised. By the way, note B, the base station antenna height was 10 meters. Now, we thought ourselves this is for an operation assistance of an autonomous car in real traffic. But what about teleoperated driving? Here are some of the use cases. So you may have a car sharing fleet which you want to optimize on farms, the tractor. You are not in traffic, you can do teleoperated driving. For an autonomous vehicle, if something goes totally wrong, what do you do? If it is in the middle of the motorway, so to say, you have to get it out. So there are many use cases where this is of interest, and you see here real pictures. We also tried this, and what we found is, again, it's very challenging because you have the mix of high broadband for the video camera transmission to the driver in the remote center, and then the ultra reliable and low latency on uplink and downlink. So what we also found is that for a human driver who is sitting then in a remote control box, that tactile feedback is very important. Then the views, if possible 360 degrees, is necessary, but to reduce the data rate, you may dynamically select them, and some other findings, but at the end of the day, this worked quite well. So you see the driver here sitting in the center. You see the car of a premium OEM manufacturer with the camera systems, and we did, in this case, speed up to 50 kilometers, so we simulated urban traffic. We had 3 high-resolution video streams, and then the real-time control data on the downlink. And what we see is that teleoperated driving, TOD is teleoperated driving. We think it's very good for controlled areas, like commercial areas, public transportation, buses, for instance, where you know exactly where they are going. A bus will not go somewhere in the middle of the nowhere. And it is, from our point of view, good to complement the intelligent cars. Here are the 4 different stages, and we are clearly here at the very beginning of teleoperated driving. Stage 4 is then really that from this control center you can do whatever you like. And the challenge is that the coverage everywhere is very difficult, as you all know. If you are in a radio research, it's very difficult to guarantee. And so in factories, as said, for public transport vehicles where you know where they are going, then it's, we think, a good idea. And finally, when you compare teleoperation vehicles on roads and in factories, then at the end of the day, they're all vehicles in the sense of a mobile robot. Now, I wanted to go a step further. I wanted to share with you our view on transportation, and this is done by a designer. I won't have the time to explain everything to you, but I think we have to prepare from our communication research that we will not stick to cars and we will not stick to trains. And my message is here, when you look, this should be, so to say, roads, streets in the air, and not only airplanes. Here we have air traffic control, but you know about the drones. I had these pictures, whether they will deliver a parcel to our home, whether, like in Dubai, they tried first time, you use a taxi, low-flying automatic vehicle. We have to take care of it, and this puts also a lot of challenges on it. And one is here, a very obvious one. All our cellular networks, clearly, are optimized for ground, base station to ground communication. It's also clear, for instance, in Europe, the EAN, the aviation network, is optimized for high-flying passenger aircrafts. And the question is now with these drones, whether parcel or passenger drones, if they go beyond 300 meters, then we think we altogether may have a problem because we cannot control them in a secure manner. One of the topics is again antennas, because we are not having optimized this. So there is a huge demand, and I wanted to share this with you, and maybe there's more research necessary of all of us together, because this system you cannot extend. It's quite old, by the way. You cannot extend to the drones in these mid-level areas. So I think the pressure, and maybe also for all our companies, the business is here for us. Now, I said when I showed this original IMT 2020 picture, this is a little bit from Industry 4.0. You may have heard many companies, including Huawei, we have founded an association for the automation industry. And now when we look into concrete use cases, for instance here, inbound logistics for manufacturing, here process automation for plant asset management and so on, they did a good work and have put in now where in this triangle are the use cases really situated, because originally there was somewhere here industry automation, and you see this is much too simplified. In reality, they are along here the right side, and also massive wireless sensor networks are here in the left corner. So the reality check shows a quite different picture. It's much more complex in a factory of the future. And what we also found out, I will show you in a minute, that hospitals in e-health have quite similar challenges. So this is now, I change now away from transport to Industry 4.0. So this is a robot, and by the way, we showed this in the Hanover Trade Fair to the German Chancellor and the German Minister of Economics. That's a tablet, and there's a ball. And the target is that the robot automatically, in a closed loop, obviously, but the computer, so to say, the control is not here. The control is in the cloud. So we are using 5G for the communication, and the target is, if you push a little bit the ball, to bring it back into the middle and to control it on this little tablet. And this is quite challenging. So we call it robot as a service, because then everything is in the cloud and the robot can be put as a service into wherever you need this robot. You may know there's then some significant differences, because today decentralized control units are usually very near to the drives, to the sensors. So if you want to do this, you are changing totally the assumptions. So more and more centralized places where the controllers are placed, not the drives and the sensors. Then, as I said, the control will be in the cloud, and also decoupling of the hardware and software. So we have shown that this is possible, and we have, I have to say, optimized our 5G experimental system for the case of low latency and high reliability. And we had some learnings. The packet sizes were, depending on what happened with the ball, very different. Cycle times necessary lower than 2 milliseconds, one uplink, 1 millisecond downlink. And finally, for sure, if you push the ball too hard, then it will fall down, because then the robot cannot react fast enough anymore. Now, another experiment with the Technical University Munich Hospital, called rechts der ISA. What are we doing here? What you see is a plastic body which is used by the medical professors to train students for surgeries. So when you look inside, there are our organs in, but it's all plastic, and so no danger, whatever you do. And what we have done is we are using a medical robot, which you can buy, a camera in an endoscope, which is used today for surgeries. And we transmit the video to a remote professor, doctor, and also we give him the chance to control this robot. And again, you see here the sketch of the technical solution. We are using our 5G experimental system. We have used different resolutions for the camera, HD and 4K. We had a frame rate between 100 and 200 hertz. And this is already a challenge for the uplink. Then the control commands, round-trip delay 5 milliseconds was okay. Also interesting, we discussed with the professors, and they said, you know, when we are in front of the patient in the operating room, there's always a little bit of mechanical delay. We are used to a little bit of delay. So please just make it not higher from the communication than what we are used to. Then it's getting, for them, difficult. And we could measure then in our system that the delay was between 1 and 3 milliseconds. So at least it is possible to do this. We want to show maybe in a medical congress this from a hospital room into such a conference center. And I wanted to share with you a very new result. We changed here to a kind of surface ultrasonic transponder. You know, when you go to the doctor, sometimes they use ultrasonic analysis. And then what we found is that the doctors, when they are remote, they are used to have haptic feedback. How strong do they push on our body, and what's the surface when they go along? And this obviously is extremely challenging. This is why I added here to the slide, the newest challenge is this haptic feedback. Obviously, we need extremely low latency and relatively high throughput, because they need this haptic feedback quite detailed. Otherwise, they say, this is not what I'm used to. So, comparison between 4G, 5G, the key requirements. One of the topics is now about the carrier frequencies. So channel bandwidth, we hope for the 100 megahertz at 3.5 gigahertz. you see the MIMO capabilities we have currently 8.8 or 4.4 at the UE, and then massive MIMO at the base stations. And now the question is, what happens if we need higher throughput? So here are the 10 gigabits per second from our original assumptions in IMT 2020 and 3GP. And our conclusion is relatively simple. We have to go to higher carrier frequencies. So maybe 28 gigahertz and then higher available channel bandwidth, because I think we cannot just overcome physics. And this is one of the topics we are working currently. Now, I talked already about antennas. So, especially with cars, this is a very sensitive topic. Why? You see here 4 antennas, as it is mostly in our cars. Sometimes they have only 1, maybe 2. And here's another sketch where they are much more separated. And here's a little bit a discussion between us and the car manufacturers. Why? They don't have space in the cars. I was not aware of this. The cars are full with all kinds of electronics and sensors and motors. I have no clue. So they tell us we have only very little space in the car. On the other hand, when you look a little bit, this is here from 3G, 4G, where we have a lot of experience. The separation of the antennas should be at least 10 centimeters, because a good decorrelation is necessary for the diversity and multiplexing techniques. Isolation of, from our view, 12 dB should be achieved in practice. And then it's really getting difficult when they are too near together. And on the other hand, the car manufacturers are saying, oh my God, how shall we put all these distant antennas in a real car, especially when the car is not this big. So, benefits. Currently, one of the big discussions is in car-to-car communication. You may know that some OEMs are preparing for 2019 to offer us as end consumer models where car communication is already in. And we are discussing currently in 5GA, which is the counterpart to 5G ACIA. If you are interested, please join us. This is 5G for automotive applications, an association, and we are discussing with the Commission how this should look like, because a delegated act is in preparation. Now, without going here into these details about the technical side, we had a look at the different positions of the antennas for car-to-car communication. And now in a single antenna communication, then it's usually assumed to do it over the roof, because you have the best view, so to say, 360 degrees around. But we could show that depending on relative position and orientation between the vehicles, are they in the same lane, are they in different lanes, are they coming onto each other, that there are also better positions. And here's a little bit from reality antenna, different antenna combinations which provide the lowest path loss. And when you look here, this is 140 meters distance, then it's about 4 dB. And I think this is already something where V doesn't sound so much, but it is much. And this was achieved by bumper antennas instead of roof antennas. So it's a critical question, where do we place the antennas and how many of them? Now I want, at the end of the talk, a little bit to go further, because so far I talked mainly about low latency, high reliability, so really, especially in cars, to support autonomous cars. We have asked ourselves now, you are sitting in an autonomous car, well connected by our 5G systems, and you go 3-4 hours in this car. What will you do? I think, first of all, you don't want to be bored, so the entertainment system is very important. But secondly, I think we are here all in the room business people. You may like to work, and you need access to the network. Now, the question is, for virtual reality, or in other words, high data rates, we have assumed here 300 megabit per second per user coming from NGMN forum. You see the sources cited. We have done here different simulations and computations, and also here over speed. So we assumed here the cars are in standstill, 10 kilometers, 50 kilometers. You see the assumptions, Madrid grid, 1,000 users per square kilometer. So you have to start with many parameters again, whether they are in reality absolutely fitting or not, we do not know. And so we use different 10, 20, 30 antenna beams, and you see immediately with speed, there is a huge drop in the mean user throughput. So this is in megabit per second. So from a macro point of view, this will only give us about 10 to 20 megabits per second per vehicle, and this is obviously a huge gap to the 300. So we think we need kind of, if this is the run today, this is the throughput, here the accumulated rate, then we need something like a kind of revolution. And the question is, how can it look like? Yeah, again, physics are somewhere in the background, so our suggestion would be that we densify instead of having macro cells. This should be depicted here, to have a continuous ultra density network where you have, at the end of the day, always a line of sight. And this is here exactly the same chart. This is again macro cell. This is now MIMO, so here 4 base stations per square kilometer. Here we have assumed 264 per square kilometer, and you see that the mean throughput is nearly independent whether you go 10, 50 kilometers or you are in standstill. And also for sure, the required density is lower if you go to out of the city. If you go to highways, then you can also guarantee and build the system line of sight. In a rural area, obviously, this doesn't make sense. So this is concentrating on cities and on highways. Now, this is Stone from Rappaport 2013. Again, here in meters, transmit and receive separation. And this is in a Manhattan grid, the parcels versus distance. And you see here different assumptions, non-line of sight, 200 meter typical macro case, 30 meter line of sight, what we would assume for a ultra-dense network, carrier frequency 28 gigahertz, and the difference is 70 dB, which is, I think, a word. According now to our computations, we think we can lower the antenna gains by 40 dB, and this makes the tracking discovery about 10 to the power of 4 times easier, and at the same time we can lower the transmission power of the base stations. Indoor, I don't need to tell you, 28 gigahertz, there is no chance, so this can only be handled by indoor access points or base stations. Now, the question is how to do this, and one of our proposals would be, why not using the street lamps? And I'm aware this is a very tricky situation, a political one, because who owns in different countries the street lamps, who is in charge of maintenance, who guarantees them, and so on. This is more from a regulation and political point quite tricky. But from a technical point, they have a lot of advantages. They have already a power cable. The site is there, so there is no site acquisition, so to say, necessary. You don't see it. Nobody may complain that there are more antennas around. You know that this is sometimes sensitive. And you even made an use the cellular network for a smart street lighting control. And here, dense network, macro, what I wanted to point out is that we think that the power, instead of 2,000 watts, 2 kilowatts, we may go down to 10 watts, which means that the power per square kilometer goes significantly down by a factor of 6 to 7. So it can be extremely low transmission power, which is, we think, a big advantage. Now, last slides. I talked a lot about radio, and what I wanted to point out is, let's not forget what's behind the base station, so to say. There is a backbone network, and there's only one slide. This is not the topic of today, but if you look into the different vertical applications, multi-broadband, the verticals, Internet of Things, we have to support by a 5G core network all these different data streams. Also, we have a lot of paradigm shifts. Cloud networking is coming up. We have software-defined networks and slicing. And the question is to reduce the cost for the operation for the telecom operator about automatic optimization. So a common core network for different applications is the idea behind it. And from especially the vertical experiences, there is now a very high pressure coming up to go into deterministic networks. If you look up here, today we may have 20% of semi-persistent scheduling for voice over LTE. 80% are not scheduled. This is for V2X, vehicle to vehicle, vehicle to infrastructure, maybe it goes up to 40%. Smart factory in the logistics, about 40%. So still 60% not critical. But then when you go down to the shop floor, this means really where the robots are and where the mobiles are carrying the different parts in the factory, then this goes probably up to 70%. And this makes then a huge change. Here's a little diagram of the cycle time in a SBS, so a PLC like the one from Siemens or ABB. Cycle time, assume 250 milliseconds necessary. You have to take into account the actor and sensor timing, and here's some processing time, and you see this is getting very challenging. So our assumption is the architecture may look like this, that we use 5G for this critical cyclic processing data to exchange the communication here between the node B and the terminal, and we leave the industrial internet, which is anyway deployed, for the non-critical, non-cyclic process data. And then as you need to have a deterministic scheduling, you will need a time-sensitive network master, which is depicted here. And this is one of the directions we would suggest for the future. So at the end of the day, when we think about the radio resource management, to have a deterministic one which can support this high percentage of necessary real-time traffic. So last but not least, I'm coming to the outlook. What do we need to address and do research further? Spectrum. First of all, I think we are all worldwide very good in sub-6 gigahertz. This is well researched. The question is about beyond, whether it's around 30, 60, 90. Then the next question is also from a regulation point of view about spectrum usage models. Not all of these frequency bands are just free, nobody's using them. Here's a whole block on antenna technology. I think this is one of the most important. We have to concentrate altogether in the future. Massive MIMO. When you look, here's an example. You go 50 kilometers with the car, you have 1.8 gigahertz. Then you need to update the channel estimate for a MIMO system every millisecond. At 28 gigahertz, every 80 microseconds. So this puts totally new challenges. And hence, also the spectral efficiency goes down. The computational load, as you have seen, increases significantly. Then in higher frequencies, there are fewer clear paths rather than the smeared conglomerates of signal paths. So the channel models, they tend to have less rich angular and delay spread. And also the question is, how good are the models? And from our point of view, a simple conclusion is that at higher frequencies, maybe beam selection is better than beam forming as the preferred strategy. And last not least, I think we all as researchers have to look into security, which I call intrinsic security. We should not prepare further for networks where we then add security. I think this is not the times anymore where you can do this. We have to think about intrinsic security. This means, for instance, to use AI to detect anomal behavior if there's something in a network going on because somebody is disturbing it or wants to take over parts, so that we can detect this. AI technology may be one. And another one is also about the management in slicing networks, how to have here clear privacy implemented, that the slices are as independent as they should be. With this, I would like to thank you for listening to me, and if you have any comments or questions, please come forward.
Thank you very much for such a nice talk, to say the least. So, a couple of questions. We have time. Anyone? Okay, the mic is coming.
Thank you very much. That was very interesting. I've got a question about your research directions and priorities for the future. You gave a few examples of innovation on 5G human factors, if you will. You talked about haptic feedback and delay in augmented surgery to support trust, I presume, and also usability and accountable, responsible use of the technologies. Yet social acceptability and societal acceptability doesn't really feature in your priorities. I wonder whether it does kind of in a tacit way, and that whether you couldn't actually put more emphasis on the fact that you're developing a human 5G connectivity.
That's a good point, and you are right. Currently, we are more looking into the technical solutions and the use cases, so to help a professor, or let's say there's a surgeon, and now he finds out, this is a very special case he has never done before, let's say to rescue the patient's life, and if the professor is 1,000 kilometers away, the expert to help here. I do not exactly know where this will go, but let me make one comparison. I think you all know that this discussion is currently a huge one about social acceptance and also regulation in AI. And the question will be, when we come near to offer these use cases, I mean, this is all research currently, then I think you are very right, and we have to think about it, whether, you as a patient, you will accept, and maybe you have to sign before, because you will be unconscious. So if my surgeon here in the operating theater does not know anymore how to deal with, I agree that 1,000 kilometers, an expert professor is taking over remote. I fully agree, but we are not yet at the point to discuss it.
One more question? Yes, please. You bring the mic there.
Hi there. You talked about densification of the network to support the higher throughputs and millimetric wave frequencies. But I was just wondering, in your examples where you had the teleoperated vehicles, is the sort of densification of the network an issue there, and what kind of site densities are needed to get the reliable link as well? Or is it just purely network coding that you're relying on to improve the RAN reliability, or is multi-connectivity included and requiring some site densification for the reliability requirements?
Right. No, what I have shown last, the densification of the network is not taken into consideration. Here we are still in a macro deployment, but you have seen from our point of view, we need to guarantee in the layout of the network that there is, wherever the bus goes, wherever in a commercial environment the vehicle goes, that there is always coverage. This is the assumption underlying currently. We cannot lose the link, then there's an issue.
Okay, thank you.
Okay, thank you. Thank you. Okay, we then move to the second keynote of today. So Biz, allow me to say like this. So Biz is coming from the United States. He's a professor at the University of California at Davis, and he graduated further north in Seattle in the University of Washington. And okay, he's bringing a different topic, but I think he's going to complement very well what we heard until now. So Biz, the floor is yours. Thank you.
Good morning, and thank you, Luis, for the introduction. And I want to thank Miha and Moita, Luis, and the other organizers for inviting me to the conference. This is my first time at your conference, and it is very impressive, particularly the demos, both in quality and quantity. And I wish I was attending earlier as well. Okay, so thank you for inviting me. Okay, as you can see from the title of my talk, there's no 5G. All of the other keynotes had 5G in their title. And I went back 5 years to 2014, and I found most of the keynotes had 5G in their title. Of course, it was maybe more proposal-like topics 5 years back, and now we're more into implementation, demonstrations, and so on. So anyway, not being 5G in the title is the first strike against me. The second thing I also looked at over the last 5 years is most of the people who are giving keynotes are from industry, except one person yesterday. So being from academia, and that's the second strike against me. And then also the last 5 years, I find most of the keynote speakers are from Europe, and maybe a few from Asia, nobody from US. So that's the third strike against me. So I'm under a lot of pressure. And today, coming from America and traveling to the other parts of the world and preaching is not a great idea either. So I'll try to do my best. But fortunately, the theme of the conference is 5G and beyond, and I'm certainly in the and beyond category, right? Okay, so you can see the title, Rising Power of the Network User. So who are the network users, right? All of us over here are network users, right? But I want to expand it. Most of us are network communications technology savvy, right? That's why we're here. But the network user, we should consider are, like your friends, who are in other fields, all of whom are using smartphones, okay? Everybody's carrying a powerful device, okay? And even after we have 5G, like yesterday when I was trying to access some mission-critical application for myself, being a professor, I had to enter the grades for my students, so a learning management system. I think for everybody, right? Whatever company you're working for, okay, you have to, do some work while you're here, and so you're trying to connect to some mission-critical or business-critical applications, and you get your circle of death. Oh, okay, the machine is thinking. So now you're wondering, where is the problem? Is the problem in the application itself, which used to be on premises, but now maybe it's in the cloud? That creates even more problems with cloud virtualization. It could be in the network. Maybe when we get to 5G, maybe the problem is not in the 5G footprint, but our application is going, many applications are going beyond the 5G footprint as well. So the problem can be in the network, or the problem can be in the network services. What do I mean by that? Well, if I want to connect to something, first I need DNS, then I need authentication, radius server, LDAP, all kinds of things, each of which is a potential bottleneck. Therefore, what we need is full visibility, not necessarily the random end user, but at least when the random end user complains to their provider, they should be able to tell in real time what is the problem, where is the problem, and be able to fix it. Okay? So therefore, when I talk about beyond 5G, I'm looking at the end-to-end network beyond the standard 5G footprint. And I would like to expand our view from a technology-centric perspective, which is what we see a lot. We already see some application centricity coming in from our previous talk and from all the panels and so on, but expand it even further into user experience, user centricity. So for a particular user that is complaining, can we say what's the problem? Or where is the problem in real time, okay? So that is the view that I'm sort of taking. And when can it be possible? I'll show you some examples, at least from an enterprise-centric perspective today, okay? But I hope, with smart devices, even the end user with a little savviness should be able to figure out what the problem is, where the problem is, and so on, okay? And with our devices being smart, whatever smart device we have, 5 to 10 years from now, it will be obsolete. There'll be even more capability, right? Can we put even more like analytics in our devices itself? Stuff coming into the device and out of the device, network traffic. There's a lot of information there, okay? Can we do deep packet inspections and try to figure out, who is knocking on my machine trying to get in and all that, So anyway, this is the theme, okay, that I'm trying to work with today. All right. So different applications have different capabilities and needs. So this is taken from Thomas Pfeiffer's slide from Nokia. So as you can see, different, some applications have very, very short latency tolerance, right? Whereas some can have much larger latency tolerance. So the main idea is that different applications have, diverse needs and characteristics, and this is the latency one, okay? So some of the computations, of course, have to be done in the edge cloud, okay, because of the short latency requirements. Latency is one. The next slide I have is a little dated from Verizon when they were introducing their FiOS. And here again, what all are the different applications, their bandwidth needs, upstream, downstream, and maybe this should be updated, okay? But I couldn't find an updated version of this kind of slide. And then on top of this, on top of this, we also have like loss tolerance, okay? Some of our applications, can tolerate losses, okay? So keeping all of these diversities in mind, okay, how do we ensure that, we can do the best job from an end user experience perspective, okay? Not just a network technology perspective, not just an application-centric perspective, but an end user experience perspective. Okay, so this is a busy slide. I got this slide from Bob Doverspike, who retired from AT&T recently. And we are putting together a handbook on optical networks by Springer. It should be coming out soon. So he's showing, these are the various methods by which you and I get access to the internet. This is the cellular network, and with 5G, maybe there'll be larger coverage, okay, that we get here. But then the truth is still that for accessing many of our applications, okay, we have to go through the other parts of the internet, the backbone of our networks and so on. And so this is the bigger picture. So we have our access networks, and then the metro core, and the intermetro, which Bob calls intermetro, but it's the backbone network, okay? Okay, So with this background, therefore, let me again reiterate, I'm looking at expanding the end-to-end picture from just the 5G footprint to end-to-end, and also looking at different applications and end-user experience. Okay. But before I came here, because the title of the slogan of the conference is 5G and beyond, I thought, okay, I should at least say something about 5G or some things that I have done about 5G, okay? But after coming here, I find, okay, I think everybody knows about these things. So anyway, I created my outline in this manner. So the first part is 5G briefing very quickly, and the network user and its growing influence, and when I get to that, I'll give a preview of that. But the most important part that I'm focusing on is this user experience, or the network user experience, using advanced network analytics as more and more of our applications and the network services are getting into the cloud and then getting virtualized as well. Okay, actually I prepared this, normally I do PowerPoint, but for the first time I tried Keynote and I was excited, but I found, okay, we can't do Keynote here. So now it's converted to PDF. And with PDF, now all my animations are gone. So any drama that I was hoping to create is not there anymore. So everything shows up, like this. Okay, so when did this? I've been working on optical network for a long time, and around 2006-07 time frame, we're like, okay, we find, the wireless network is being operated independently, the optical network is operated independently. There's no tight coupling. And we all don't want to be tethered, but we want high capacity. We want the high capacity of fiber to come as close to us as possible. So therefore, how to create a converged architecture, okay? And that is what we wrote up in this paper, Wireless Optical Broadband Access Network, or WOBAN. And then it was like dormant for a few years, this field. And then we saw activity on fixed mobile convergence, wireless wireline convergence, 5Y, et cetera. And now they form the underpinnings of the fiber front haul, really, in the access network. Okay. All right. I think you know about these, so I will not talk about these. I'll not talk about these. So significant contributions from my lab on this ultra densification about virtualizing the DU pools and so on with the Cloud RAN architecture, which is what this looks like. So DU Cloud has the computing resources, the front haul with its optical fiber provides our bandwidth resources, and then the radio resources are close to the user. But everybody knows about this. I'll skip this. And more recently, from my lab, these are some works that have appeared. 5G front haul, latency and jitter studies of CIPRI over Ethernet, and then TDM-EPON front haul, upstream capacity improvement via traffic classification and sifting, okay? All right, enough about my 5G briefing. Okay, so the network user and its growing influence. And what I want to do is a little bit of a historical review as well about how carriers and infrastructure providers have evolved in their thinking over the last 2 decades, let's say. And until around 2000, 2005, carriers were the main dominant forces. And an example that I'll take is about providing resiliency or redundancy, okay? So carrier will say, I'm going to provide you a lot of capacity, okay? 100 gig capacity, well, those days, let's say 10 gig capacity between point A and point B. And if there's a failure somewhere, I'll fix it in 50 milliseconds, okay? So it was a very, very network-centric view, right? But then, after a while, as we start putting our information in the cloud, in data centers, our objective is, hey, the network can be dead, but my information should be available, right? So the trends evolved, okay? And so this is what this timeline is showing. So cloud networks or cloud service providers started appearing, and then we find more application-centric networking. And today, user experience for network users is becoming more critical. Okay, so this is where my animation got lost. So traditional view before we had the cloud was consumers like you and I get services from enterprises, which in turn run their network connectivity over carriers. But now with cloud service providers, we have a lot more opportunities with virtualization and creating virtual slices out of physical resources and so on. Okay, so this, again, without animation doesn't work out so well. But here what we are showing is, we can actually have disaster zones. There can be multiple locations where we can have problems that might break because of natural disasters or because of human-made disasters. So there's primary path, there's backup path. There can be multiple backup paths, okay? See the animation, it's gone here. So instead of having, so you can have a primary data here, the backup data here, they're in different data centers, but if they're too close to each other, that's not good because a single disaster event might kill our connectivity to both. So you might want to have backups in disaster disjoint data centers, okay? Okay, again, it doesn't look too good, okay? All right, so now we are focusing on the network user in the era of the data deluge. Users are not patient anymore, they require prompt services, or else they move to alternate sites or apps. So again, this is where I was coming to, if I see the circle of death, okay, that's not very good, and the problem should be resolved quickly, otherwise we lose the user to the competition. Okay, and some of these aspects have already been covered by other speakers where the edge cloud servers, okay, can handle many of our tasks that are very, very latency sensitive and have very, very tight latency constraints. Okay, all right, so moving to the last part of my talk, which is what I'm most excited about presenting. Today, what do we have? Actually, let me go to the next diagram here. So this is how an application-centric infrastructure for a business looks like today. So a business can have a main office, many branch offices. They can be connected to the internet. A lot of people are using SD-WAN technologies as well to choose between various connectivities, data rates, providers, etc. Traditionally, all the stuff, the data centers were on-prem, and also the network service functions like DNS, LDAP were on-prem, but now we see more and more of the data, of the applications moving to the cloud. In fact, about 5 years back, in my university, the student information system, which used to be on-prem, was moved to the cloud by the provider of this service because they had 50 other clients and it made more sense for them to have one instance of this student information system. But then the problem was, okay, now the traffic that our students, myself, staff, we're generating is stomping over various internet domains on which we don't have control. We don't have visibility. So therefore, at least in their case, it became very important to figure out if there's a problem, which domain is causing the problem so that we can complain to them, or which router inside which domain is having the problem. Maybe some router is dropping a lot of packets. Maybe some link is having excess delay, too much congestion, etc. And now we find even the network functions, like DNS, LDAP, they're moving to the cloud, like radius servers and so on. And then, of course, there's the third-party applications for two-factor authentication or billing and all of that. So therefore, we can have problems anywhere. And to figure out where the problem is becomes challenging. So your main office can actually be covered by a full 5G network. Each of your branch offices can be covered by your 5G networks, okay? And if, and maybe you have enough capacity there and no issues, okay? But there can be problem anywhere over here. Okay, so what tools and techniques exist today to handle an issue, okay? So if an employee is unable to access the business critical application. So today, when we have a critical application not working, it takes many days to root cause because there are multiple teams involved, there's guesswork. So the application people will say, hey, my application is working fine. The network guys will say, my network is working fine. But we know that, if you say my network delay on a certain link is so much, my packet loss rate on a certain link is so much, that doesn't really mean anything because for different applications, there can be different tolerances, right? So an application-centric view, therefore, is very, very important. Okay? And current network layer solutions address one service or device like DNS or a specific router and so on. So there are APMs, application performance monitoring tools, okay, that will tell you if the application in the data center is working properly or not. And today's applications are actually getting more and more distributed, okay? The front end can be on-prem, the back end is in Amazon. They can have, even the back end can have multiple components, and they can be dynamic. Dynamic in the sense that, I can have a database, or I can have an application that is using a database which uses, let's say, 8 virtual machines at 9 a.m. in the morning. And these virtual machines are spread over 3 servers in one data center. As the day progresses, as the load increases, as more demands come in, this database might have increased to 25 virtual machines spread over 8 servers, spread over 2 or 3 different data centers in different geographical locations. So how do you actually chase an application which is expanding and contracting, okay? And my view is that by monitoring the network traffic here and here, okay, and doing deep packet inspection, okay, I can figure out for my main mission critical application, okay, where are the corresponding endpoints, and as they're expanding and contracting in real time. And that is very important for me to get the full end-to-end visibility of how my application is running. Because now if a user, if an employee is complaining, I can figure out which of these VMs they are accessing and what is the problem that they're having. Okay, so that was about the APM focus, application performance monitoring. And there are the leading APM vendors are like AppDynamics that Cisco just acquired for $3 billion, more than that. New Relic and Dynatrace and so on. All right, and then we have these NPMs, network performance monitoring devices, which will tell you how your various routers are performing, how, what's the performance on each of the links, packet loss ratios, delays, packet forwarding rates, and so on. But that doesn't tell you the full picture. Again, the NPMs are application agnostic. The APMs are network agnostic. what we need is full visibility. Okay? NPM, APN combined together is not going to do it either, because they'll not be able to track these activities, these network functions that are cloud virtualized, third-party applications that are also in the cloud, okay? Okay, some of you might have seen this chart from Gartner Blue Planet, and I find it very interesting about analytics and progression of analytics. So let's say this is current time, okay? So descriptive analytics is what happened. Do I have enough forensic information to go back in time and do network time travel and figure out what happened in the past? Okay? Diagnostic analytics is, why did it happen? Okay? Creating insight. Why did it happen? Predictive analytics is what will happen. So now we are getting into a futuristic scenario. And prescriptive analytics, how can we make it happen? In the sense we want to be prepared. Contingency planning. Okay? Can we simulate extreme scenarios and see how the system will react and be prepared for it in advance? Okay? So therefore, with respect to analytics, hindsight, the past, insights, sort of the present and near future, and foresight is, extreme cases, okay? How might we be able to prepare ourselves? Okay, so now this problem that I was speaking about here, right? There can be a problem anywhere, okay? I would like to be able to show on a single pane of glass all of the possible issues that might occur. And one of the things I have to do, so I'll now talk about technology challenges, and I'll have 5 of them. Most of them are application and end-user centric, but some of them are also like server-centric in the sense that, if the bad guy is trying to break in or doing something not usual, can we detect some of that as well? So we're not necessarily doing security, but we want visibility. We want full visibility into what's going on, okay? And we'll create baselines of normal behavior, and it'll be adaptive. For example, what I mean by adaptive baselining is, if I look at the triple bridge, okay, how many people pass over it? If I say on an average day, 10,000 people are passing over it, that's not good information. I would like to know at 12 noon how many people are passing over it versus at 1 a.m. how many people are passing over it. Maybe at 1 a.m. people are still partying, so a lot of people. And I would like to know, what is normal at different times of the day and what are deviations from normal, right? And so that is what is adaptive baselining. So to do many of these things, okay, we need some important tools and techniques. You can call them machine learning or you can call them whatever, okay? But the idea is, how can we figure out in real time, okay, what is the most useful information that should be provided as visibility to the owner of the critical application? Okay, so this technology challenge is automated discovery of app service topology. So let us say we have a group of users, okay, and let's say this is the main office. There are some critical applications. In this particular case, there's one critical application that they're accessing. While doing that, okay, they are relying on various other network services. Okay, you can see DNS here, Kerberos, SSH, LDAP, etc. Remote procedure call for this. This is a file sharing application. So they also have SMB for server message block, transactions, all kinds of things are going on here. So this topology, as to when an end user is accessing, recursively these other network functions are being accessed, and if any of them is not performing properly, this guy will see circle of death, not working, okay? So should we just conclude that the application is down? Or if you have a mechanism which tells you which part of these network functions are underperforming in real time, that would be most useful. So doing this in real time with the huge volumes of data that we have is the challenge, and that is where this kind of solution, which we call the causal dependency graph, becomes useful. Okay? So it's like an art to figure out which technique to apply to which problem, right? So the causal dependency graph comes in very handy in creating this so-called app or application service topology. And this will evolve, okay? If I look at it 24 hours later, it would have evolved, okay? Because maybe the current users, okay, are doing some additional stuff which are invoking some other functions, okay? And these lines that you see, these are logical links, but they can actually be paths going over several domains, several routers, because many of these functions are also cloud virtualized, okay? So the next diagram that I'm going to show you, okay, is automated path performance mapping. So from various locations that I have, let's say I have an enterprise with many branch offices. I would like, and my main application is in the cloud, in some data center. In this case, there's only one location, but with time, it can grow to multiple different virtual machines. But anyway, how to figure out what all are the various paths, what all are the various domains, what all are the routers in each of these domains, what's the performance of each of these links, to be able to continuously baseline them as to what is normal, and then to flag something that is significantly deviating from the normal. So if the delay over here is significantly high, I'll make this red, okay? If this router is dropping a lot of packets, okay, I'll make it red. If the end-to-end delay from, let's say, from my main office to the server is much larger than what is normal, okay, this will also be flashing in red, okay? And if I had my own laptop to give a presentation, I spoke to Mukherjee the other day, then I could show you in real time, okay, a demo. For my particular university, they have like 200 different endpoints in which they're interested because they have a lot of traffic going to these endpoints, okay? Amazon, GCP, Azure, and Apple, and various other institutions where we have, relationships, okay? So technology we call, for uncovering these paths, we call packet train technology. So now imagine for your enterprise, okay, if you want to know the 10 or 20 important paths over which your traffic flows, would you like to know how those paths are? It's like a Google map, but only restricted to what your interest is. You can specify those 10 endpoints in advance or 100 endpoints in advance, but you don't have to. You tell me that, by monitoring the traffic, look at what all are the top 200 flows from my main office to whatever endpoints are there across the internet, okay? We can figure out and tell you how these paths look like. Okay, so this is where the user situation comes up. So app-specific user experience analytics, so multi-layer contextual correlation. And what we're showing here is that some user, whose ID is Celston7, okay, is having some problem right now, okay? Is the problem in the application, in the network services on the network? We find it is in the application. And this particular, and the network is fine, delays are fine, losses are fine, bandwidth is fine, they're not doing any jitter, and services we are not showing here because there was no such issue. But when you troubleshoot, okay, you find abnormally many canceled errors in SMB2 change notify transactions. Abnormally many no such file errors in SMB2 query directory transactions. So in real time, we are able to catch these scenarios. And now if the employee complains, say, my file system is not working, what's going on? You look at, if you're the application owner, the IT guy, you look at this, you say, are you trying to access an application, a file that doesn't exist? Okay. Or are you trying to download a directory and you don't have permission? Okay? And of course, there can be issues in the network as well. Okay? So any of those issues can happen, and we should be able to tell our employees in real time. So this is the timeline. The time bar shows 6 hours right now, but you can go up to 1 month, okay? Because all the data is there. And even beyond, okay, if you create your own tertiary database. Okay, so this is what I meant by user experience analytics, okay? Okay, this diagram shows volumetric analytics, app specific. So we do multi-dimensional macro flow clustering. So this is a server. How much traffic is going into the server? And these are the various clients. How much traffic are they all taking out of the server? So here again, if you see something abnormal, and I have seen something abnormal. I mean, for a particular application, this is a file sharing application. Okay, not a file sharing. It was a financial system. Yeah. Financial management system. So normally, everything is for each connection is like 70 megabytes or 100 megabytes, something like that. Suddenly, I see half a gigabyte of information flow, exfiltration. Okay, isn't that funny? So the network has so much information. By doing appropriate analytics, we can get this visibility. Similarly, this financial management system is supposed to be accessed only by employees of the company who are, they may be traveling, yes, okay? But sometimes when we get connections from rogue domains, that is suspicious, okay? So this is where, the visibility can lead to some, I won't say security, but, more knowledge about what you may have to do to write additional rules for your firewall. Okay? And then automated anomaly detection and pattern recognition. So AI-based inferencing using parametric regression, model-based health scoring, random decision for too many jargons and so on here. But again, adaptive baselining, is the key. Okay? I'm getting almost to my time. So in summary, advancing network technology is great. This is what we're doing with 5G. But getting application centricity is important, and we see some of that already. But making it useful to the random user, your friends who are not networking specialists, okay, is, again, I think very, very important so that we can have more value creation, okay? So desired features, analytics-driven visibility for the network topology, app service topology, traffic clusters, automated anomaly detection using adaptive baselines, heat maps, events, ensuring we can meet end-user SLAs using application delivery, path performance, user transaction response analysis, and forensics, current performance as well as historical performance, and network time travel, all on a single pane of glass, okay? So I'm sorry if I disappointed you, if I didn't talk too much about 5G, but I addressed more of the end-to-end scenarios, and I addressed more of application and end-user analytics, okay? And if you are interested in learning more, do let me know. Actually, I can go to the next slide, yeah. I would like to be able to partner with some people here to understand newer use cases for your scenarios so that we can make this activity more useful. Thank you for your patience.
Thank you. I can imagine you have a couple of customers for this app on the user experience, right? Because you can really see where the problems are. So, a couple of questions. Anyone? Let's see. No? Okay, is there? Sorry, yes, the mic is coming.
Thank you very much. Could you say a bit more about the relationship between automation and visibility? Because oftentimes security or functionality is, the zero touch, and the more automation you have, the safer and the faster systems are. So making them visible to experts might be very helpful, but making them visible to my friend or even to me, that means nothing, and I would not be able to do anything. So people would just want things to work. So if you could say a bit more about that, that would be helpful.
Very, very good question. So right now, what you saw is, meant more for application users, application owners, and the network operators and the CISO type guys. Okay, I would like to hope that eventually, further enhancements can be done so that a random end user can be told with a little bit more intelligence, okay, as to what's going on, where the problem is, and so on. And with respect to automation, some things can be learned, like what all are the various endpoints, okay, that the traffic emanating out of your main office are going to, and we can do that. Sometimes even the fixes can be automated, but we are very wary of that because the people that we work with, they want to do it themselves. So we need to sort of take, the second last step and tell them, I think if you do this, your problem will be solved, rather than taking the last step of automating. Thank you.
Any other question? Yes, Alex?
Very interesting talk.
Thank you.
Just a simple kind request. If the user-centric view is becoming more and more important, in my simple-minded view, also means that this view has to be better mapped into requirements and facilities at the application fabric, as well as the network fabric, and both in a multi-heterogeneous environment. Question is how to do that well. In other words, how to make sure that the end-user viewpoint is finally reaching 5G, because this is a big question.
Yes. So I think that's a very good question. And when I showed the end-user analytics, that's actually drilling down from top. It's not that you want to see that all the time. Okay, so the topmost information would be like a time bar, which shows you alerts, critical alert, warning alert, or maybe the application owner, gets these alerts. Okay, and then they can drill down and look for what exactly happened. So that's the first part. And the second part, I think you're right. How can we use this information to feed back in order to be able to do better designs? Okay, and I haven't thought much about it. I think it's certainly a very important aspect that needs attention.
Okay, thank you very much, Ben.
Okay, thank you. Thank you.
Okay, just a few housekeeping things before we break for coffee. Just a reminder of, we have the banquet tonight at 7 at the hotel, which is 10 minutes walk from here. Then you can and you should still vote for the best booth until 4 in the afternoon, right, Mich? It's until 4. You can do it via the app. You can download the app to, you know what this is, right? So just download the app without still the user analytics, without still 5G, but it works. So you can vote with the app. I think you can also vote with paper. There are a few paper, this 19th, 18th century technology, whatever it is, that is still available. And also there is the feedback form. So we'd like to hear from you what you liked and what did not like about the conference. And you have it also on paper, on the tables, and also via the app, and also on the website. So just give us your feedback. Thank you for coming. Enjoy the rest of the conference in the coffee break. Thank you.